Hello, today we are going to solve a university question. It is the problem of a stepped bar. I'm going to solve this problem in a step-by-step methodical manner. I will try my best to demystify the concepts behind this problem. Okay, this can be very helpful for your university examination, but it just requires a bit of practice. Okay. The first step to solve this problem of a stepped bar, the first step in any finite element analysis problem is discretization. So the first step, step number one, is always discretization. Here we go. So I'll write discretization. Discretization is the word that is used by finite element analysis engineers because I don't think you will be able to find the dictionary meaning for the word discretization. I don't think it is available in Oxford English dictionary. I just once checked. So discretization specifically is the word that is used by finite element analysis engineers. Okay. The discretization is the breaking down of the structure into known geometric elements, and for those elements you readily should have the formula for stiffness. Okay, I mean you should readily have the formula for stiffness matrix. Okay, that is discretization. It's no confusion. Here we go. It's a simple problem. I'm going to divide this given bar into two elements. Of course, this is going to be element number one, and this is going to be our element number two. Now, why? Obviously, you can see that the cross-sectional area changes. So definitely when the cross-sectional area changes, I should discretize there. That should be a different element. Just for example, I will do one more example here. Suppose there is a bar where the cross-sectional area is not changing, but there is a load that is acting here. Then again, I have to say this should be element number one, and this can be element number two. Okay, and I can say that suppose there is a bar where the load is acting only at the free end, but in between the material changes. So the Young's modulus for the two is going to be different. Again, I have to discretize this into two elements. So these are just examples on how you actually discretize this. But once you have discretized the structure, then you can mark the nodal points here. So I will represent that by green color here. This is going to be our nodal point number one. This is going to be our nodal point number two. And this is going to be our nodal point number three. I hope that three is visible. All right. So the first step, the process of discretization, is over. I'll just put a tick mark for the first step. I hope everybody is able to understand the process of discretization. You are given a structure. The first step is always discretization if you are trying to solve an FEA problem. But understand this, there is in software, the software you try to do this problem by using a software can readily discretize this into thousands or even millions of elements, depending on the type of workstation that you are using. Okay, now we are trying to do this problem manually. We will restrict ourselves to discretizing this into two elements. All right. The second step, here we go. Step number two is to find the stiffness matrix. The stiffness matrix is always denoted by the notation K, and I'm putting a square bracket there, which means that it is always a square matrix. And I'm going to find the stiffness matrix of individual elements. So I'm writing K individual. So I'm going to find the stiffness matrix of individual elements. So that is going to be my step number two. So step number two is to find the stiffness matrix of individual elements. And we're going to find the stiffness matrix of element number one. We're going to find the stiffness matrix of element number two. So here we go. The formula for stiffness matrix of element number one, it is K followed by, I'm just putting the number 1 and putting a circle there, which means that I'm trying to find the stiffness matrix of element number 1. The formula is A1 E1 divided by L1. That's the formula for stiffness. The formula for stiffness matrix, it is 1 minus 1 minus 1 1. So there is a separate derivation behind this formula. I have derived this formula already. If you want, you can check this. I can give the link in the description below if you are very curious. Okay. Now you know the value of A1. It is 2500. It's given here. It is an mm square. And the value of E1, that is Young's modulus 1, that is given in the problem. It's not mentioned. It is given in the problem, the value of E1. I will mention that here. It is 80 into 10 raised to the power 9. 10 raised to the power 9 Newton per meter square. So all I have to do is plug the value of A, E, and L. The value of L is 400 mm. Okay, that is given. Now you should be careful about one thing, that is about the units. You have to be very consistent in using the units. Now the value of area is 2500. It is in mm raised to the power 2. The value of length is in mm. However, the value of Young's modulus is not in mm. It is in Newton per meter square. So let me convert that. The value of Young's modulus, I will convert those values into Newton per mm squared. It is 80 into 10 power 9 Newton per meter square. How much is 1 meter? 1 meter is 10 power 3 mm, but there is a square there, meter square there, so I'll put 10 power 3 the whole square. So if I solve for this, I'll be getting 8 into 10 raised to the power 4 Newton per mm square. In exactly the same manner, if I just try to find out the Young's modulus value for element number 2, I'll be getting 2 into 10 raised to the power 5. Obviously that is steel. Young's modulus value of steel into 10 power 2 into 10 raised to the power 5 Newton per mm square. Okay. Now if I can substitute the value of AE divided by L, and if I just try to substitute those values of AE divided by L, it is 2500 into Young's modulus for element 1, it is 8 into 10 raised to the power 4 Newton per mm square divided by L1, which is 400, that is the length for element number 1, followed by 1 minus 1 minus 1 1. Okay, if I just simplify this, I'll be getting okay, let me do the calculations, but I want you to try and give this a shot and see what is the value that you are actually getting. I think you should be getting 5 into 10 raised to the power 5. So that's the value that you should be getting. So what I will do is I will keep this 10 power 5 outside the matrix. 5 into 10 power 5 is what you are going to get. And I will bring the 5 inside the matrix. So I'll be getting 5 minus 5 minus 5 5. Okay. So that is going to be the stiffness matrix of element number 1. So it's going to be 5 minus 5 minus 5 5. Now one thing that I used to do is what are the degrees of freedom that are pertinent to element 1? The displacement of nodal point 1 is given by U1 and the displacement of nodal point 2 is given by U2. So the displacement of nodal point 1 is U1 and the displacement of nodal point 2 is U2. I used to mention this, the one that I have mentioned by yellow color. I used to mention this so that I can easily assemble my stiffness matrix, because as I delve deeper into the subject matter, my stiffness matrix actually grows in size and I should be able to assemble the stiffness matrix in a very, very conducive manner. And this template, what I mean by template is the one that I have mentioned yellow in color. This template helps me to assemble the stiffness matrix in a very, very conducive manner. So this is the stiffness matrix of element number 1, and let us try to do the stiffness matrix for element number 2. Not try, but we are going to do the stiffness matrix for element number 2. So the formula is A2, you know where the story is heading. It is A2 E2 divided by L2. It is 1 minus 1 minus 1, 1. You have got all the ingredients that you need to know in order to find the stiffness matrix of element number 2. So let me write the value of stiffness matrix for element number 2 without any further delay. If you just try to find the value of A2 E2 divided by L2, you know the value of A2, it is 600, sitting right here, it is 600. You know the value of E2, it is 2 into 10 raised to the power 5 if you just do the unit conversions. And the value of L2 is 300. I just did the calculations, and if you just plug those values, the value that you are going to get is 4 into 10 raised to the power 5. So what I will do, as is the usual case, I will keep the 10 power 5 outside this matrix, and I'll bring the 4 inside this matrix. It's going to be 4 minus 4, it's minus 4, 4. As is the usual case, I have to mention the templates. The templates are the displacement of nodal point 2 is U2, and the displacement of nodal point 3 is U3. So U2, U3, U2, U3. These are the displacements that are pertaining to element number 2. So I'll show you element number 2. Displacement of nodal point 1, it is U1. Nodal point 2, it is U2, and the nodal point 3, it is U3. So obviously for element number 2, the displacements are U2, U3. Okay, fine. Now, what is the next step? So this is step number 3. I'm going to do the step number 3 now. So here we go. Step number 3 is to find K global, which is to find the global stiffness matrix. In order to find the global stiffness matrix, what I will do is I will first construct a global stiffness matrix. I will first construct the size of the global stiffness matrix. You see, the size of the global stiffness matrix is going to be exactly as the size of the degrees of freedom of the given system. In our case, how many degrees of freedoms are there? Well, there are 3 nodal points, and each nodal point can get displaced along only one direction, and that is along the x direction. Okay, 3 nodal points, 1, 2, 3, and each nodal point can get displaced along the x direction. So obviously there are 3 degrees of freedom. If each nodal point can get displaced along the x and y direction, then you will have for each nodal point 2 degrees of freedom. So if you have 3 nodal points, the total number of degrees of freedom is going to be 6. So clearly it is the degrees of freedom, total number of degrees of freedom in the structure that determines the size of the stiffness matrix. So the size of the stiffness matrix here, guys, it's 3 bar 3. So let me construct a 3 bar 3 matrix. And remember one important thing, that is, I have kept 10 power 5 outside stiffness matrix of element number 1. It is mandatory, absolutely mandatory for me to keep the size of the stiffness matrix. I'm sorry, keep 10 power 5 outside the stiffness matrix of element number 2 also. You cannot just keep 10 power 5 and you cannot keep 10 power 4, because our assembly then becomes a complete mess. So make sure that when you do this problem, the term that you keep outside the stiffness matrix should be the same. Okay, so I will keep 10 power 5 outside the stiffness matrix, and let me represent the assembly here. It's very, very simple. The way you assemble, let me represent by blue. You take this. Let me construct the stiffness matrix. I mean the template. It's going to be U1, U2, U3. It's going to be U1, U2, U3, and it is easy to assemble the stiffness matrix. All I have to do, I'm going to draw a blue square here. And after drawing the blue square, what I will do is I'll take the stiffness matrix of element number 1, and I'm going to fit right in the blue square. So here we go. Stiffness matrix of element number 1 is 5 minus 5 minus 5, 5. So what I will do, I'm just going to fit right there. It's 5, okay, 5, it's minus 5, it's minus 5, it's 5. That's it. Okay. Now what is the next step? I'm going to construct another square. This is a green square. Here we go. Green square. And all I'm going to do is take the stiffness matrix of element number 2, which is 4 minus 4 minus 4, 4, and I'm going to fit it in the green square. So exactly in that fashion. So let me do that. So without further delay, so maybe I can use a different color. I will use yellow. Here we go. It's plus 4, it's plus 4, it's minus 4 there, it's minus 4 and 4. So let me repeat the concept. First, I have constructed the blue square. Take the stiffness matrix of element number 1, fit it in the blue square, and I have constructed a green square there. Take the stiffness matrix of element number 2 and fit it in the green square. And whatever terms that are not filled, all you have to do is put 0 for the term that is not filled, because their stiffness matrix do not exist. Okay, so this is going to be our global stiffness matrix. So step number 3 is global stiffness matrix, and it is over. Now let me do step number 4 now. Step number 4 is to find the global displacement matrix. So I would say that it is U global. Okay, let me write that properly. It's U global. So U global. And what is the global displacement matrix? It's very simple. It's the easiest step. You see, many times they will not even do this step. It's not actually required, but we just want to do it in a very, very methodical manner. So the displacement matrix, it's U1, U2, U3. That's all. It's simple. Now, why it is U1, U2, U3? Because you are just mentioning the degrees of freedoms of the nodal points. That's it. Okay, fine. That is step number 4. And step number 5 is also quite easy. Step number 5 is F global. I'm going to find the global force matrix. The global force matrix should be the assembly of a uniformly distributed load, and the load due to temperature, and the load due to point load, or the concentrated chunk of point load. Now the force matrix, since we have only point loads, our problem becomes very, very, very simple. For uniformly distributed load and uniformly varying load, you have to come up with the formula for the force matrix. But since we have got only point load, our problem becomes very, very, very simple. In future, we will also do problems on uniformly distributed load. Okay. Now, the problem of the point loads, it's very simple. What is the point load that is acting at nodal point number 1, that is F1, and what is the point load that is acting at nodal point 2, that is F2, and what is the point load that is acting at nodal point 3, it is F3. So let me do that. What is the point loads that are acting? Let me go back to the problem. There is a point load that is acting at nodal point number 2, and which is 20 kilonewton. It is given here. It is 20 kilonewton. So let me represent that. The point load that is acting at nodal point number 2, it is 20 kilonewton, and that is going to be, it's nodal point number 2. It is 20,000 Newton. Okay. And what is the point load that is acting at nodal point number 3? It's 5 kilonewton. So it's going to be 5,000 newtons. So I'm just trying to be consistent with the units. Is there a point load that is acting at nodal point number 1? Any point load should be acting at nodal point number 1. Well, there is a point load that is acting, though it is not mentioned here. Because nodal point number 1 is fixed, there is going to be a reaction at nodal point number 1. So that is denoted by R1. This is very important. Some people put 0. If you are putting 0, it's not an accurate representation. Okay, so our step number 5 is over. Okay, step number 6. Step number 6, very easy. Step number 6 is you are going to substitute, take lift and substitute the value of K global, because you have computed that, and the value of U global. You have also computed the value of U global and the value of F global. You have to take this and substitute this in the global finite element equation. So that is finite element equation. And what is the global finite element equation? It is very simple. It is K global multiplied by U global is equal to F global. So this is our global finite element equation. All I have to do is take those values and plug it here. Mathematics is like moving objects now. So what is our K global? So here we go. Our K global is here. See, it is 5 plus 4. So that would be 9. Okay. So let me remember that. So let me take this K global and put it there. It's going to be 10 power 5. Okay. It's going to be 5. Well, it is a 3 by 3 matrix. Okay. It's 5. It's minus 5, 0. See, always this K global, K matrix always is a symmetric matrix. So if you are done with the first row, the first column is going to be exactly the same. It's minus 5, 0. This trick is going to be extremely useful if you want to solve higher order problems. This is going to be extremely useful. And the second term is 5 plus 4. It's 9. It's minus 4 because of symmetry. If this is minus 4, then this should also be minus 4, and the last term is 4. This is K global. Followed by U global, it is U1, U2, U3, and followed by F global, and F global is R1, and what is the value of R2? It is 20,000 Newton, and this is 5,000 Newton. All right. If the force is acting in the opposite direction, please put negative sign, guys. Okay, this is step number 6, and now I'm going to do step number 7. And what is the step number 7? It is to apply the boundary conditions. Apply the boundary conditions. BC denotes the boundary conditions, and this is one of the coolest steps. And the boundary condition is, what is the nodal point that is fixed? It is nodal point number 1. So what I will do is I will cancel the first column and the first row throughout. And one of the reasons why I'm saying this is because, you see, obviously this term U1 is going to be 0. If U1 is going to be 0, if you try to do the matrix multiplication, you will end up with 3 equations, but you have only 2 unknowns, U2 and U3. Why do you need 3 equations for 2 unknowns? It's not necessary. So what you will do is you will just put U1 as 0, or you can, instead of doing the matrix multiplication, before you do the matrix multiplication, get rid of the first row and the first column. Those are the rows that are pertinent to the nodal point number 1. So you don't need 3 equations in order to solve 2 unknowns. The problem becomes it becomes superfluous data. Okay, so you apply the boundary condition, get rid of the first row and the first column because U1 is going to be 0. So this is how you apply the boundary conditions. So in the next step, you convert this into algebraic equations. But before I do that, this is one step that people used to forget, and that step is you should take this 10 power 5 to the other side. So you have to take this 10 power 5 to the other side so that you get 20,000 divided. If you take this 10 power 5 to the other side, you get 20,000 divided by 10 power 5 and 5,000 divided by 10 power 5. So obviously you will be getting here 0.2, and in this case you will be getting 0.05. Now it becomes easy for me to convert this into algebraic equations. So let me multiply this matrix with this matrix so that I convert this into algebraic equations. So I'll be getting 9U2. If I do this matrix multiplication, I get 9U2 minus 4U3 is equal to 0.2. And if I just multiply the second row and hit it with this column here, I'll be getting minus 4U2 plus 4U3 is equal to 0.05. You can use your calculator to solve the 2 equations, but anyway, I'll be getting, if I just add the 2 equations, I'm going to get 5U2 is equal to 0.2 plus 0.05, that's 0.25. And you are going to get the value of U2 as 0.05. 0.05. If you just work out the value for U2, you are going to get 0.05 mm. So that's the value of U2, and you can just plug the value of U2 in one of those equations to get the value of U3. And the value of U3 will be, if you just solve it, 0.0625 mm. So I got the value of U3. Okay. All right. So after getting the values of the displacements, so this is going to be, so I think I forgot to mention the steps here. This is going to be our step number, this is going to converting the algebraic equations. This is going to be our step number 9. So I'll say this is step number 8, 7, and you take this 10 power 5 to the other side. If you want, you can consider that as step number 8, taking this 10 power 5 to the other side. This can be our step number 9, which is to convert the matrix into algebraic equations, All right. Now, the next step. Once you have got the values of displacements, now you can find the strains and the stresses. I don't think I'm interested in strains. All I'm interested in is finding the stresses. So let me write the formula for stress. The formula for stress is D matrix into B matrix into U matrix. This is true for any finite element analysis problem, guys. You have to remember this. D matrix is the stress-strain relationship matrix. It is simply Young's modulus. And B matrix for one-dimensional element is -1 by L, 1 by L. And the U matrix, suppose you are finding the stress for element number 1, the displacement matrix will be U1, U2. If you just hit this matrix with this matrix, so you will be getting Young's modulus into U2 minus U1 divided by L, which is simply Young's modulus, which is the strain. Obviously, it's Young's modulus into strain, right? So this is for element number 1, and you know the Young's modulus for element number 1. It is 8 into 10 power 4. If my memory serves me right, you just got the values of U2, U1, and the length for element number 1, which is 400. Okay, this guy is 400. So you got all the ingredients, guys. I don't have to do this mathematics. You know where the story is heading. So the stress for element number 1 is, if you just compute, its value is 10 Newton per mm square, and that seems to be a very small value. I think our material is going to be safe. If it is within the safety limit, of course it's going to be safe. Quite axiomatic here. And similarly, I can find the stress for element number 2. Let me do that in the next page. Stress for element number 2, it is going to be D matrix into B matrix into U matrix. If you just work it out, it is Young's modulus for element number 2 into U3 minus U2 divided by L2. If you just plug all those values, I will leave that to you. You are going to get the value of stress for element number 2 as 8.33 Newton per mm square. Not only they have asked the values of stresses in the question, they are also asking us to find the values of the reactions. This is crucial. And this is how you find the values of the reactions. So let me do that here. Okay, it's very simple. The global stiffness matrix is 5, it's -5, 0, it's a -5, 0, it's a 9, -4, -4, it's 4, followed by U1, U2, U3. The value of U1 is 0, and the value of U2 is 0.05, and the value of U3 is 0.0625 is equal to the values of the forces. It is it's R1, it's R2, which is 20,000, and the R3 it is 5,000. I'm sorry, not R2, R3, it's F2, F3. The forces at nodal point number 2, 3. All I have to do is find the values of the reaction R1. So all I'm going to do is hit the first row with this column. Okay, let me do that. It's going to be 10 power 5 And all I need to do is multiply the first row with this column. It is 5 into 0, then minus plus of minus 5 into 0.05, okay, plus 0 into 0.0625, just elaborating that things here, is equal to R1. If you just work out the value for R1, so these two terms are 0, you are going to get, if you just hit it with 10 power 5, you are going to get minus 25,000 Newton. This is a very cool answer that we are getting, because what is the total load that this bar is subjected to? It is 20 and 5. The value is 25 kilonewton, which is 25,000 Newton. And I am getting exactly the same answer here. It's minus 25,000 Newton. The minus sign indicates that it is going in the opposite direction. So this is how you compute the reactions. I hope you're able to understand the step-by-step methodical manner by which we can solve this problem. Okay, in future we can solve the problems of uniformly distributed load. So that's uniformly distributed load for a bar, and the problems of beams we can continue to solve the university problems. Thank you all for your patience. Thank you so much.